All right, let's jump right in. Today, we're going to look at two super useful, but sometimes overlooked tools for understanding your data: the QQ plot and the stem and leaf plot. You can think of them like special X-ray glasses for your numbers. They let you see the true shape of your data. And trust me, that shape can be the difference between a solid analysis and one that's totally off the mark.
So why do we even care about the shape? Well, it turns out that a lot of the big, powerful statistical tests, the ones that help us make major discoveries, have one really important rule. They assume your data follows a specific pattern, something called the normal distribution. If your data doesn't follow that rule, well, your conclusions could be built on some pretty shaky ground. The real question is, how do you know? How can you tell if your data is actually playing by the rules?
So, here's what we've got on tap. First, we'll talk about those hidden assumptions lurking in our data. Then, we'll spend a good chunk of time on the star of the show, the QQ plot, and learn how to read its diagnostic line. After that, we'll check out the brilliantly simple stem and leaf plot. And finally, we'll wrap it all up so you know exactly which tool to grab from your toolkit and when. Okay, so let's get into it. This normal distribution, it's really just a fancy term for that classic bell curve you've probably seen a million times. And this shape is a huge deal because so many things in the real world, like people's heights or even tiny errors in measurements, naturally fall into this pattern. Because of that, a ton of statistical models are built with the assumption that your data looks like a bell curve. But here's the catch. If you try to use one of those models on data that isn't shaped that way, your results can get seriously skewed. It's really like trying to force a square peg into a round hole. It's not going to work right.
And that leads us to the big problem, right? You can't just glance at a column of numbers in a spreadsheet and go, yep, looks like a bell curve to me. Our eyes just aren't built for that. We need something more reliable, a visual tool that acts like a truth detector for our data's shape. We need to be able to ask our data, point blank, are you normal? And that is exactly what our first tool is all about. So, let's talk about the main event, the Quantile-Quantile plot, or as everyone calls it, the QQ plot. This is really the gold standard for visually checking if your data lines up with that all-important normal distribution. It's a much more sophisticated and precise way to check this assumption than just looking at a simple histogram. So what in the world is it? At its heart, a QQ plot is basically a face-off. It's a graph that pits your data against a perfectly normal distribution to see if they look alike. It does this by comparing their quantiles. Now, don't let that word scare you. You can just think of quantiles as a more general version of percentiles. They basically slice up your ordered data into equal-sized chunks. The plot checks that the slices from your data match the slices from the ideal bell curve.
So here's the game plan conceptually. First, the plot draws a perfectly straight diagonal line. This line is our benchmark. It's what the data should look like if it were perfectly normal. Next, the computer crunches the numbers and finds the quantiles for your actual data. Then comes the comparison. It plots your data's quantiles as a series of dots against that ideal straight line. And the last step? That's your job. You just look. Do your dots hug that line or do they veer off course? The answer is right there in front of your eyes.
All right, this is probably the most important part. You've made the plot, you see the dots and the line, now what? How do you actually translate that picture into a clear answer about your data? Everything, and I mean everything, hinges on this straight diagonal line. This is our ruler, our ideal, our North Star. In a perfect world, if your data was a textbook example of a normal distribution, every single one of your data points would land smack dab on this line.
And this is what you're hoping to see. This is a pass. When your data is normal, or at least close enough, the points will line up really nicely, almost like they're tracing that diagonal line. Sure, they might wiggle around it a little bit, but the overall trend is unmistakable. A picture like this is your green light to go ahead with those statistical tests.
But what if you see this instead? Any kind of clear, systematic deviation from the line is a major red flag. If the points snake away from the line in a curve or an S shape, that's the plot telling you something is off. It's screaming, hey, your data is not normal, it's skewed, or it has heavy tails. It's a clear signal that your data has a fundamentally different shape. So let's just make this crystal clear. The interpretation here directly tells you what to do next. Points on the line, it means your data passes the test. You can feel confident moving forward with models that assume normality. But if those points are deviating, you gotta hit the brakes. That's a critical stop sign. It tells you to either try to transform your data to make it more normal, or, better yet, switch to a different kind of model that doesn't care about that normality assumption at all.
Okay, let's switch gears to our second tool. We're going from a really precise diagnostic test to something a bit more like a quick sketch. It's called the stem and leaf plot, and I love it because it's like taking a quick x-ray of your data. To see how this works, let's use a really simple data set. Here we have the exam scores for 20 students. Right now, it's just a table of numbers. It's pretty hard to get a real feel for how the class did or where the scores are clustered just by staring at this, isn't it? And boom, here's the plot. It's actually super simple to build. We just split each number into two parts. The stem is the first part, in our case, the tens place, and the leaf is just that last digit. So that score of 65 becomes a stem of 6 and a leaf of 5. The scores 72, 74, and 78 all get grouped under the stem of 7. Simple, right? But here's the really cool part, the aha moment. If you literally turn your head to the side, what do you see? It's a histogram, a bar chart made out of the actual numbers. You can see the distribution and every single data point at the same time. Pretty clever.
So we've covered two pretty different ways to look at our data. One is this highly precise diagnostic tool, and the other is more of a quick and dirty sketch. The real skill is knowing which one to pull out of your toolkit for the job you need to do.
Let's just break it down one last time. You're going to reach for the QQ plot when precision matters, when you absolutely need to check for normality before you run a big, important statistical model. But you'll use the stem and leaf plot for smaller sets of data, when you just want a fast initial feel for how things are laid out without losing sight of the original numbers. At the end of the day, both of these plots help us do one thing. They help us listen to what our data is trying to tell us. They reveal these hidden patterns that are so easy to miss when you're just looking at a table of numbers. So the next time you have some data in front of you, don't just see the numbers. Remember to ask, what's its shape and what story is that shape telling me?